This is a real pleasure for us at Drakai Capital to have the opportunity to present part of the research project we are undertaking. So for this today presentation, we will focus on this research, which is entitled Enhancing Long-Short Portfolios, a Refined Approach Using Learn-to-Rank Algorithms. So this research has been written with my co-authors, as you said, Thibaut Metz, Khalil Sbai, and Guillaume Boulanger. So this is the agenda for today. First, I will introduce the research topic, outline our motivation, and explain the framework guiding the study. Then we'll talk about the main issue relative to some learn-to-rank loss functions. More precisely, we'll see that these loss functions display an asymmetric shape, undermining downstream portfolio performance. So in this part, we will consider a synthetic data experiment and provide a high-level description of the mathematical proof. In a third part, we propose improvement over the classical learn-to-rank loss functions in order to correct this asymmetry, and we will validate the approach over synthetic data again. And in the fourth part, we will validate our approach over real-world data. And finally, we'll be concluding. So let's start with a quick intro. Here, I would like to describe the framework we consider for this study. So this is represented in the figure that you can see here. So when relying on machine learning models for portfolio construction, we often rely on a two-step approach. So first, we provide features and labels, and train a supervised machine learning model in order to predict what are the future expected asset performances. And then, thanks to these predicted scores, we need to go to a real portfolio allocation. And so to do so, we provide the predicted scores to a portfolio construction algorithm. So it's often an optimization under constraint, possibly including, for instance, investor preferences. So these two stages are often treated independently, so limiting potential synergy. Nevertheless, in the literature, we see some efforts to merge these two steps into one cohesive system. So either having one whole machine learning model directly predicting portfolio weight, or a multitask model, for instance, both learning asset performance and optimal allocation. Okay, but in the case of this paper, we won't try to unify prediction and allocation, but instead consider this standard framework, this standard two-step process, and show that the choice of the supervision, so the first step, and particularly the training loss, can embed some biases that can undermine the downstream portfolio performance. As I said before, we'll be focusing on the learn-to-rank loss functions. So indeed, some studies have shown that this loss function can outperform classical regression-based models for cross-sectional asset ranking. Usually, the learn-to-rank loss functions are classified into three groups. So first, you have the point-wise loss function, where assets contribute to the global loss function independently. For instance, mean squared error. You have pairwise loss functions, where we focus on the relative ordering of asset pairs. So here we really want to push away the scores of assets that are very far away in their true ranking. So these losses, they use the idea of relative ordering between pair of assets. And the last one is the listwise loss function. And so this is the score of each asset relative to all the other assets, okay, that contribute to the overall loss function. So in this approach, we consider the global ordering, okay, of all the assets we consider. So in this work, in this precise research paper, we focus on the last two categories that are the most interesting ones. So namely, we will investigate RankNet for pairwise loss function, and ListNet, ListMLE, and ListFold for the listwise loss functions. And so just to finish on this slide, the core setup that you need to keep in mind for this presentation is the following one. We use a learn-to-rank loss function to train a machine learning model, whose scores are then fed into a long-short portfolio construction. And from this setup, we then assess how the shape of the loss function can impact the portfolio performance. So all the research we undertake at Drakai Capital comes from real-world issues we encounter. So here I split it between business challenge and scientific questions. For us, the business challenge is that we know that long-short portfolios, long-short strategies need to clearly identify over and under performers. But we saw that learn-to-rank loss functions can emphasize either the top or the bottom element of the ranking list, which limits the portfolio performance. So we aim to adapt the classical learn-to-rank loss functions to better highlight the extreme of the rankings and finally better serve the long-short portfolio constructions. And the scientific questions are more concise. There are two main questions we try to answer. The first one is, do classical learn-to-rank methods introduce asymmetry biases that favor either the top or bottom ranked assets? And the second one is, do our improved loss function lead to better financial performances on real-world data? So now, first, let's talk about what we mean by asymmetry bias in learn-to-rank loss function. First, to exhibit the asymmetric learning of the different loss functions we consider, we rely on a synthetic data experiment. So we generate an array X of size 300 by 74 by 62, thanks to a uniform -1 + 1. And then we compute the Y as a closed quadratic sum of the X. Okay, so here, 300 represents the temporal dimension, 74 the number of assets, and 62 the number of features describing each asset. So here, for this synthetic data experiment, the choice of 300, 74, and 62 was to mimic the real-world data we'll be using later on. And I want to emphasize also that the shape of this array does not matter that much. And so for the model, we use a multi-layer perceptron with layers 136, 272, 34, and 1, and ReLU activation function in the hidden layer. And we use a sigmoid activation function for the output layer. So we'll be training this model for 4,000 epoch and a batch size of 32. Again, the choice of the network structure and we take does not matter that much, but we wanted to take the same network as the one introduced in one research paper from 2021 by Xia and Al. And this is the research paper introducing list fold. So you will see after that we kept their data for our real-world data analysis. So we kept the same network structure. So now, most importantly, which is very important, is that while training the model, we will track along all the 4,000 epoch the loss value and the top K accuracy separately for the top 10 elements and the bottom 10 assets. Okay. And for robustness, we average these metrics over 100 runs. So just to sum up, our main goal here is to show that the different loss functions tend to specialize either in predicting the top assets or the bottom assets more accurately. So this is a synthetic data experiment to try to show first this behavior. So here are the results we get. So you can see, for instance, that for the pairwise RankNet loss function, the learning seems symmetric. So this is the first graph. So indeed, we see that along epoch, the loss value here in green is decreasing, meaning that the model is indeed learning something, hopefully. And we end up with an almost 70% accuracy for the top and the bottom element the last epoch. Okay. And for the three other list-wise loss function, we see that it's not the case. For listnet here, we see that the ranking ends up predicting with a better accuracy the top 10 elements than the bottom ones. For the list MLE, this is the reverse. We see that the model is better at predicting the bottom elements than the top ones. And finally, here in the fourth graph for list fold, so this is the third asymmetric case, we show that the accuracy for, so here we, just to explain to you, we show the accuracy for each group of 9 elements. And we see that the model is learning well how to rank assets at the extreme of the ranking spectrum, so which is good for the downstream long-short portfolio construction, but it's also learning well here to classify the middle of the list, the middle element. And assets, these assets, we don't care that much about them because they won't be that much traded in a long-short portfolio. You tend to trade the extreme of your ranking. So here you can see that each of the three list-wise loss functions displays a different kind of asymmetry, which intuitively is not good for a perfect long-short portfolio. So after having exhibited the asymmetry relying on synthetic data, in this paper we tried to show mathematically that an asymmetry indeed exists. So here I will give you a sense of how we tried to show it. The main idea is the following one. We explain the asymmetry by comparing the penalization of the loss function for the exact same ranking error at the top versus at the bottom of the list. Okay, so let me develop a bit. Let's consider a vector A of perfectly ranked scores. Okay. From this vector A, we build two new vectors, okay, one H and one J vector, by either swapping, so by swapping two consecutive elements, either at the top of the list, so for the vector H, or at the bottom of the list for the vector J. The hypothesis which is very important here is that the error in H and J should be of the exact same magnitude. Okay. So once we have these three vectors, so A perfectly ranked vector, H vector with an error at the top, J a vector with an error at the bottom of same exact magnitude. So thanks to this list, we were able to compare delta LH, which is a difference in loss value between the list with an error at the top and the perfectly ranked list, and delta LJ, which is the difference in loss value between the list with an error at the bottom and the perfectly ranked list. So again, I highlight the fact that we do the hypothesis of the exact same ranking error at the top and the bottom. So once we have these quantities, we are able to develop the loss function in order to compute this delta LH and that delta LJ, and we get the following results. For RankNet, as we saw with the synthetic data here, we see that the delta LH equal delta LJ, meaning that there is no asymmetry. For ListNet, we see that delta LH is greater than delta LJ, meaning that the loss function is penalizing more when we make an error at the top of the list. So this explains why this loss function was specializing more into predicting top element in the synthetic data experiment. And for list MLE, this is the reverse. We see that delta LH is lower than delta LJ, meaning that the model will be trained more on not doing error when predicting scores for bottom assets. So this mathematical proof here is to confirm the observation made with the synthetic data experiment. So we see that the bias in learning of the list-wise loss function come from their analytical form. Okay.
So, excuse me. Can we ask questions at this point, or should we wait till the end? I don't know quite how these sessions work.
I think maybe I let Horst answer, but I think it was at the end, just to be sure we finish in 30 minutes. But I don't know.
Yes, I think that since we have interrupted, we can carry on with this question from Professor Engel.
Okay.
I'm sorry. What did you say again?
No, please go on with the question, because in any case, now we have made the break, so we can go on with this question, please.
So by the way you've designed the data, there is a nonlinearity between the features and the performance, which means that the extremes in the upper tail will be more sensitive to the features than in the lower tail, as I understand it. I would suppose that might be the opposite of what we would think in the real world, that maybe the negative left tail is usually the long tail in empirical distributions. So if you turned it around, would you get sort of the same results?
We will be talking about it later on real-world data, I think. But yeah, as you said here, the way we built the synthetic data experiment, for me, it's perfectly symmetric. See here, we take the x as a uniform between -1 and 1, and after you compute the y as a quadratic closed form of them. So here we can just say that the distribution is symmetric and center 0. Okay, but I agree with you that the quadratic form maybe can highlight more in the y, the extreme of the ranking spectrum. So this is true. Here you will see that we take real-world data later on. We didn't investigate that much the distribution of the return, but this is true, and your point is very right in the sense that here this is the part of the research, but at Drakai Capital we work on credit products, which are often very skewed, okay, non-linear, and yes, of course, we take this kind of non-linearity, or let's say non-asymmetry in returns into account. I don't know if this answers your questions, more or less, okay. But yeah, we didn't look that much. If your question was about saying if we tested it with different distribution of returns, for the synthetic data experiment, not. We take this very simple case because our goal was to check the classical loss function with the improved one we will introduce later and see if in a perfect case scenario, we can do better. So this was the first part to try to understand how it works in a perfect world.
That's fine.
Okay, let's move on, and I'll give you extra 5 minutes. So we're turning to the general question answer at 35 minutes past the hours. Okay, back to the presentation, no Mathis. Please go ahead.
So having said that, let's try to improve over the classical loss function that we see have an asymmetry, as we just said, in a perfect world. You have very nice returns. Okay, so as you understand from now, our main goal is to correct the asymmetry shape of this loss function so that there are more efficient in classifying assets for building long-short portfolio. So now I'm going to present to you the modification we bring to this classical learn-to-rank loss function, introducing list-net fold, list-MLE weighted, and list-fold weighted. Okay. So the goal here is not to go that deep in the mathematics, but it instead gives you a sense of how we modified this loss function. But before starting, let me introduce to you some notation. Let's define as X the array of objects to be ranked, Y the ground truth scores, so the labels we use to supervise the learn-to-rank model. We state that if YA is greater than YJ, it means that XA is ranked above XJ. Okay, and we also denote Y minus 1A, the index of the asset as the ES true position. Okay, so F is our function model, and so as every supervised machine learning model, we aim to find the optimal F, minimizing the loss function based on X and Y. Okay. So here, for the first one, you can see list-net, the classical one, and the second loss function is our proposed list-net fold loss function. So the classical list-net loss function formulates as a cross-entropy over the scores of assets, with phi being an exponential here. So the bias in list-net more learning how to rank top elements precisely come from the exponential nature of this softmax function. So to fix this issue, we propose a modification of the list net inspired from a list fold. So instead of considering each asset individually here at the numerator, we'll consider the difference in scores of each pair of assets. So by adopting this approach, we utilize and we rely on the list net imbalance, focusing on enhancing rankings at the extreme while deprioritizing pairs in the middle. So in other words, here we really want to push away the scores for pairs of items that are at the extremes of the ranking spectrum. So now let's move on to the list MLE loss function, which was the second one for which we saw a bias. So you will see that for the last two loss functions, so list MLE and list fold, we try to counterbalance the learning asymmetry by adopting a weighting scheme here with lambda A in order to prioritize the assets to classify well. So for list MLE, the ranking bias comes from its sequential nature. Intuitively, here you can see that the list MLE loss function, so for this loss function, you can see that the elements at the bottom will account more into computing the overall loss function. So this is the second sum that you see here. First, you sum over all the elements from A equal 1 to n, and after from k going from A to n. Okay. So to counterbalance this, we introduce a lambda A, signifying the importance of accurately predicting the rank of the highest element. So this is again to emphasize the top ranked items, so enhancing their contribution to the overall loss function. And finally, let's see our modification regarding the listful loss function. So this loss function was introduced in 2021 by Xia and Hall in their paper published in Quantitative Finance. So as you can see, this loss function unifies the pairwise and listwise approach in a sense. So indeed, it considers differences in scores for pairs of assets and takes these pairs from the most extreme ones to the middle pairs. Okay. So here we propose listful weighted. Here again, we introduce a lambda A representing the significance of accurately predicting the rank of the most extreme pair of assets. Okay. So now we want to check if our new proposed loss function seems to reduce the asymmetry bias during the learning process using the exact same synthetic data. So we take again our synthetic data and we trace the same model with the new loss function, aggregating the results again over 100 runs. And as you can see, this new loss function seems to reduce the learning asymmetry. So for listnet, for listnet fold and listml weighted, we can see that the accuracy for the top 10 elements is approximately the same as the accuracy for the bottom 10 elements over all the epoch. Yeah. And for listful weighted, we can see that at the end of the training, extreme groups of assets display the best accuracy, whereas before both extreme and middle assets display the same highest accuracy. So just to sum up what we did so far, first we defined the asymmetry bias from the learn to rank loss function, both mathematically and using synthetic data. Then we proposed improvement over the classical listwise learn to rank loss function and checked the validity over synthetic data again. And now in this new section, we try to see if this improved loss function work as expected in a forward testing setup and relying on real world data. So you will see later, but we'll assess the quality of the different loss function out of sample. So both looking at ranking and financial performance metrics. So for our real-world data experimentation, we use the same data as the one introduced in the paper of Listfold, published in 2021. So this data is available on GitHub. It's made of weekly equity observation from the China A-share market, mostly listed in the HS 300 index. So the size of the sample is about 620 weekly observation across 74 stocks, and each stocks being described as a set of 62 factors. So we aim at ranking assets at time t thanks to their weekly returns over the next week, so at time t+1. And the period covered by the data spans from December 2006 to February 2019. So now I will describe our training and forward testing procedure. So at each time t, we consider the last 300 weeks, we standardize the data, and we train the model. Then we skip the following week. We scale the data, and we predict over the next 16 weeks, which constitutes our test set. As I already mentioned before, for the purpose of quality, we didn't employ any validation set here, but we relied on the exact same model and hyperparameter as the one introduced in the paper by Xia and al. In 2021. The validation here was not very useful because we really want to compare the different loss function ceteris paribus. So the same model, initialization, hyperparameter, and so on. So finally, getting our out-of-sample prediction, we build a long-short allocation with weights decreasing linearly to emphasize extremes. So k equal 10 means that we will be longing 10 assets and shorting 10 assets, for instance. And on each half, for the long part and the short part, we will invest $0.5. So we didn't take into account, So we did not take into account transaction cost or the other hypotheses because once again, we're interested in showing that our method surpasses the classical ones instead of interpreting the performance per se. Okay. So now let's look at the performances of the different loss functions. So we both look at the average ranking and financial performances, building a K long-short portfolio for K going from 1 to 10. So for the ranking metrics, we consider the information coefficient, the Kendall-Tau, and the weighted Kendall-Tau. For the weighted version of the Kendall-Tau, we rely on a quadratic weighting to emphasize extreme. So as we can see here, the IC and Kendall-Tau are not always better. You can see it here. For new loss function, meaning that the overall ranking is not always improved. But we can notice that the weighted Kendall-Tau is better for proposed loss function, meaning that the extreme of the ranking spectrum is better predicted. So this is aligning, obviously, with the objective of building a long-short portfolio. So now going to the financials performance metrics, we can notice that our enhanced loss function seems to perform better for a wide set of financial metrics. So this is supporting again our analysis of an inherent bias contained into classical listwise long-to-rank loss function when coupled with a downstream long-short portfolio construction. And here, even more visible, we display the average weekly returns for K long-short portfolio with K going from 1 to 37. So this clearly shows that once again, our improved loss function emphasizes better the extreme than the standard loss function. So each time for each heat map on the right-hand side, you have the improved loss function or modification. On the left-hand side, the classical ones. Also, as you can see for list MLE weighted, which is this heat map, we can see that when longing shorting 37 elements, so half of the whole portfolio, the average weekly returns are worse than for the classical list MLE, meaning that the overall ranking is worse. This is aligning with what we saw right before here. Okay. And finally, we display the last graph in the research on real-world data. We look at the temporal average PNL of K long-short portfolio for K going from 1 to 10. And again, with the goal of comparing the classical loss function with the improved ones. And we can notice here again a substantial gains relying on our corrected loss functions. So now I will conclude. So regarding the academic contribution, we tried as much as possible to characterize the inherent ranking bias of some classical listwise run-to-rank loss function. So both mathematically and relying on synthetic data. We then propose enhancements over this loss function to try to attenuate these biases. And finally, we validated our findings using open source data, showing that this new loss function allow to improve the financial performance of a downstream long-short portfolio. And regarding the business size, so of course, it can equip quantitative researchers with new tools to improve their machine learning models. But most importantly, in this research, we really wanted to highlight the importance for the data scientists to have a critical view when building a machine learning based trading system. And more precisely, we really wanted to say that the choice of the machine learning model should be in adequation with the downstream portfolio allocation method. So to me, this is of huge importance in a RIA where modern libraries make it very easy, to swap loss functions or algorithms without always having to implement them and deeply understand them. So finally, here are some references we use for the presentation, and now feel free to ask questions.
Thank you, Mathis. So I'd like to open for questions and ask all the reviewers to use the raise the hand feature. And the first question, hand is up by Marcus. Marcus, please go ahead.
Thank you, Horst. And thank you, Mathis, for this presentation. It's a really interesting paper. You present two types of evidence to assess this model. One is based on the synthetic data, and that's very clear, interesting, and congratulations on these results. However, you also ran a walk-forward backtest and report the performance of that backtest. And whenever I see a backtest, I always wonder how many backtests did you run in parallel, and how do you address the issue of performance inflation as a result of selection bias?
Yeah, so I tried to answer this question and maybe talking about the approach we have at Drakai Capital. So each time we want, because we are not trading this kind of assets at Drakai Capital, but each time we start a research, we try to look, as we show on synthetic data, to understand the real behavior. After we try to understand it mathematically, then we take open source data. So in this case, we took the exact same data as another research paper introducing listfold. And but this is not at all, we are not trading equity at Drakai Capital. And right after, if we see that it seems to work on data we are not trading, then we go with our internal data. So our internal data that we own, we built, and there we test again this approach because here this is a real change in methodology. And if again in our internal data it seems to work, so on completely different asset and way of building, because here I just take the next weekly returns, which is very simple. We have our own way of supervising models, but we take it on our internal data, and if it works here, I say we hope that it will work in the future. But this is our way to do it. So for this one, just for the question of this paper, we just take the same hyperparameter than the other research paper, which is not a very nice answer, you can say. But for internal point of view,
yes,
can hope that if it works on the other data, synthetic data, and we understand it mathematically, and that it works on our internal data, we can hope that it will work. But I say we hope.
And I understand that you as a practitioner of course, you will run additional tests in order
to exactly.
Get. But as it relates to the paper being a claim on its own right, what I would have liked is to see some adjustment to the reported performance. So that could be done either estimating a family-wise error rate or estimating a false discovery rate, or applying some alternative method like Romano-Wolf, given that Michael is in the call, or using White's reality check. There are so many alternatives, and I feel it's a bit of a missed opportunity, meaning that you have done such a great job explaining the method, developing the mathematics, presenting evidence based on synthetic data, and then it just leaves this aftertaste of the backtest is presented and is presumably based on the best results that you got. So why not to take the extra step to deflate those values? So, but that's perhaps that's just advice for the future. All right, thank you. That's fine with me. Thank you.
Thank you, Marcus. Then the next hand up is Michael Wolf, please. Go ahead.
Okay, well, thank you for the talk. Very interesting. I have a few comments on the backtest. I think there's value in using a data set that's already there, perhaps, but this one, it seems just a bit short. I think the auto sample period is about 6 years, and you have weekly data, and it's really hard. If I look at that last exhibit, there are like 3 colors, red, blue, and green. And I would sort of guarantee with the red and the blue, you will never get any statistical significance, no matter what you test. The green maybe, but the red and blue, I mean, the point numbers may be different, but any test would not reject the null that
I agree.
The two performance is the same.
Yeah, I agree. But the thing we tried again to try. This is something you don't see here because we did a lot of runs, but here we try to show the confidence interval. You have the blue and the small blue. So in the synthetic data part, we try to see statistically. See, for instance, here we just computed a confidence interval about the average of the accuracy for the top 10 and bottom 10 to see if clearly on synthetic data you have significant difference between the accuracy on the top element and the bottom ones. Okay, but on real world data, I agree. We try to be as much as out of sample as possible. But I agree with you that for me, the important in this paper was to really try to see it on synthetic data, show it mathematically. It's a bonus to show that it's working on real world data. But again, we do these 3 steps, and after we put it internally with our internal data, and if it works.
I think synthetic data, you can sort of construct the data a bit to your liking, and most people might be more interested in real world data.
I agree. Yeah.
Okay, and the other one, because you had the K was ranging from 1 to 10, and then you present average results over K. I'm not sure that makes sense for all the different performance measures, right? So averaging certain performance measures over different values of K may or may not be meaningful.
Yeah, but this is to try, because, if I present you the data saying, okay, I took a K equal to 6, you will say why you took 6. So here we just try to average the performance data, taking to be as fair as possible regarding the different loss functions. That's why we took a different K. Because this is an hyperparameter to cross-validate, but as a practitioner, when you try to explain a research thing, you can always push more and cross-validate something else. But this is part of a big assumption we did. I agree with you. Yeah.
Thank you.
Ben, thank you, Michael. And then Rob, next question.
Thank you. This is I thought, a very interesting paper. I guess I'd like to think for a moment more about the symmetry that you're trying to achieve between the long and the short end. I mean, it's not totally clear to me that symmetry is the ideal criterion for what a better estimator ought to look like. And maybe we're more interested in the short end or in the long end. And this would be probably something that would depend on the utility function that you expect your client to have. And, ultimately, this strategy has got to be compared with its risk. So if you look at the risk over different portfolio strategies, you're going to have to decide sort of what aspects of risk, what utility function you really want. And so I'm not sure that your first slide kind of suggests maybe you need to do all this at once. And maybe that is still ultimately where this you want to go with this, so that you can do risk and return both effectively.
This is a nice a nice comment because basically we publish in your journal a second paper, which is which is this one, unifying asset ranking and portfolio weighting through multitask neural network. Because after publishing this paper, we were asking, okay, how to choose the K, how to do the decrease in the portfolio construction, how to make the loss function of your learning algorithm talk. Here we're just stating that, okay, if you have one team doing the machine learning model and the other one doing the portfolio construction, just be careful because it may be good to have a synergy between the two. And in this other research paper, we try to have a kind of one unified framework to both learning the rank and also choosing, depending on your investor preferences, how to choose a number of assets to long and short, how to weight your final portfolio allocation. This is what we try to do in this paper. And here we look, as you said, as how this unified framework behave if you have a more risky client or less risky portfolio, how it behave, depending on the preferences of your investors, or the final strategy you want to build. Sorry, this is not an answer, but this is an extension of what we did in the exact. This is exactly what the question we ask and what we try to answer in this one.
Thank you.
Next one.
Thank you. So I don't see any more hands up. So I'd like to ask the reviewers to raise your hand and speak up if you have any more questions. Okay, George, yes, has the hand up.
I got a short one just for future reference. I know it's only a detail, but I can't help myself. The MSE is not a loss function. It's a risk function. So it's the expectation of a loss function. So it's just as a mathematical statistician, it goes against my
okay
sensibilities.
Okay, sorry. As a guy using scikit-learn often, we rely on maybe this is how I usually name it. Yes, it's just the square of error you do and you supervise your model via this function. Yep. Take your point.
Thanks for this point, Michael. And George, a question.
Yes, thank
you. Your mic is off.
Yes, thank you very much. It's a pleasure to be here. And I was wondering if you'd like to say, in your opinion, what are the weak points of your approach? I mean, what are the, let's say, assumptions that can go violated if one try to implement this for a broader setup?
As the first question was, here we took the very simple assumption first of a perfect long-short portfolio that does not, I mean, we don't, yeah, you hear me? Yeah,
yes, we can hear you.
We didn't, of course, you can have, depending on the kind of, the way you supervise your model, you can have some different empirical distribution of your return or any things you want to supervise. So here we just took a very simple example of a perfect long-short portfolio. So this is one thing which is a strong assumption. And the second one is not an assumption we made, but I agree with you that we could, if we had more time, and this is what we did, our internal framework, but here for this research, we could have extended the paper, working on different distribution data, maybe having, here we work with weekly data, maybe having daily data, you know, try to stress the model and the systems to understand more in which case this does not work. But intuitively, I would say that you still want to have a symmetry in your learning algorithm. So yes. So I would say in the practical part, how we cross-validated it, maybe we could be more out of sample validation of the different models, and maybe trying different portfolio allocation schema. Okay, because here we just do a linear decrease. Could maybe have some other allocation functions here.
Okay, thank you very much.
Thank you, Mathis. And let me ask one more time for questions. No more hands up. Last call. If there are no more questions, then I'd like to thank the reviewers who joined us from far away, from early morning to late night time zones. Thanks for being here. And I would like to thank Mathis and his team at Drakai for their presentation and for sharing their research with us. With all this, then I will turn the recording off, and I just want to remind all of you that you had been recorded. In case you were not here in the beginning, I just getting a reminder that I have to remind you that you have been recorded.
Okay.
Thank you, and a good afternoon, good evening, and a great Monday wherever you are, in which time zone. And we will be back on Thursday for paper number 3.
Thank you so much, host.
Thank you very much.
Thank you.
Thank you.
Great job.
Bye to everyone. Nice to see you all. Bye-bye. Bye-bye.